Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. Science is the great problem solver, one of the very best in humankind's toolbox. Problem solving may not always be easy, but thanks to science, our perception of what's possible continues to broaden each day. Quantum is a great help to a great problem solver. This still relatively new facet of science, depending on who you ask, is leading to new solutions in computing, simulation, and communication. What was unimaginable 30 years ago is today reality. Quantum's influence extends from our homes and our workplaces to all reaches of our future. Quantum devices are even available commercially. Consider picking up a chip-scale atomic clock or a quantum well infrared photodetector for a loved one this holiday season. As if solving ordinary problems isn't hard enough, the challenge facing our guest on All Things Photonics today involves solving problems that aren't yet fully understood. As a physicist in the DEVCOM Army Research Laboratory, Dr. Kevin Cox is tasked with protecting the modern warfighter from threats that may or may not exist. Yet another area of quantum science, quantum sensing, is his focus. In our conversation, we speak about the challenges facing our soldiers on the ground. We also get a sense of the electromagnetic environment in which soldiers are operating, and how quantum sensors fit into that reality. Operating at this ultra-high level of science requires more than brilliance, as we find out. It requires patience. Time, patience, and commitment. To us, that sounds fair. If we can't yet articulate a problem, who are we to expect to have a solution in hand? Photonics Media News Editor Jake Saltzman and physicist Kevin Cox from DEVCOM Army Research Lab are up next.
So we'll be talking about quantum sensing quite a bit today, but I think before we do that, before we even define that, we should look at some trends, the impetus behind some of this work. And we'll start in national defense and security, certainly two big drivers of the current direction of quantum sensing innovation. But for you, how do you define that direction?
I work at the Army Research Lab, and at the Army Research Lab, I would say one of our goals, maybe our main goal, is to take foundational extreme science and make it very useful for our soldiers and for our warfighter and the men and women who are going out there and doing it. So, I would say our direction, let me say, within that, I study quantum physics. That's my area of expertise. So my direction is to say, how can I take the unique properties of quantum mechanics in a way that will give a transformational capability to the soldiers, maybe in the near term, maybe in the next few years, or maybe in the long term, in the next 20 years. So that's pretty broad, but that really is our mission. That's my mission in my job.
So one of the key considerations for the modern warfighter, and it's something you've explored quite a bit, is the current electromagnetic environment in which our soldiers are, I was going to say beginning to operate, but are now probably fully operational in. How are the needs and concerns of the modern warfighter, of the soldier on the ground, evolving in response to that environment?
This question is, I would say as a physicist, this is a question that I've been, and everyone in my group, we've been working hard to start to learn the answer to that question. What are the actual challenges that soldiers face? And I would say there's a few really big picture things that we know. We know that the battlefield is becoming kind of meta, right? But it's coming at, knowing what's behind a wall, or, seeing what someone's doing a long way away, or detecting their communications, or, really using the electromagnetic environment or even the cyberspace environment to gain some advantage. And, that's as much now of the battlefield as the actual physical battlefield.
Quantum sensors can be ultra-cold atom-based or photon-based. In application, there are advantages to each. These advantages depend on the distinct physical construction of the sensor. Different sensors measure different forces. Different compositions make different sensors. Some examples of sensors that can qualify as quantum include magnetometers, used to measure magnetic fields, accelerometers, used to measure acceleration, and gyroscopes, used to measure angular velocity. Of course, as Dr. Cox explains, not all atomic quantum sensors use ultra-cold atoms, and there are some advantages there.
So I want to ask a technical question. Can you walk through the differences, commonalities, nuances with what is called ultra-cold atom-based quantum sensing and that which we would consider photon-based quantum sensing? Aside from the nominal difference, what are some of the distinctions between the two that might create an advantage for one over the other?
So to me, I mean, maybe we have to back up a little bit. Just, to me, a quantum sensor is anything that relies on a quantum particle to sense some external variable. And the really distinguishing feature of all quantum sensors, whether they use atoms or photons, is that they're limited by quantum noise, that basically that these particles are quantized, hence the name. And when you measure them, you have fundamental noise from the collapse of the wave function, of the quantum wave function. So I would kind of, again, say that there are great commonalities between all quantum sensors and that they are all limited by the fundamental collapse of the wave function. And the collapse of the wave function of a photon is really not that different from the collapse of a wave function of an atom. I should mention that in my lab, all of our quantum sensors do not actually use ultra-cold atoms. All of the atoms we're currently using for quantum sensing are room temperature, which means they're flying around at about 300 meters per second in a little glass cell. And we interact with them for the short amount of time as they fly through a laser beam. We also have ultra-cold atom technology in our laboratory where we trap the atoms inside of a laser beam and cool them down so that they're not moving at all. But actually, most of our quantum sensing work right now is using the warm stuff, which is easy because it's smaller, requires less lasers, it requires less big vacuum chambers that are very specifically made. But in reality, these atoms are not so different from photons. One way that they are very different from photons is that they interact with the world around them more strongly. If a photon collides with another photon, you know what happens? They just pass straight through, right? Star Wars isn't real, right? Like, in Star Wars, the lightsabers, they clash and they make a loud
might be
noise.
the biggest revelation we've had on all things photonics in 4 seasons.
In reality,
continue.
the lightsabers, we want to know, what are those lightsabers made out of? Because it's not normal light, right? Because normal light, they would just go straight through. But there we go. This is hard-hitting stuff. That's why we use atoms to detect fields. Atoms make some of the very best magnetometers, so detectors of magnetic fields and detectors of electric fields, because the atoms interact electrically with everything around them. And so that is, one reason that we typically use atoms for a lot of these sensors. Photons make great gyroscopes, right? Because there's not an inherent electrical or magnetic interaction in that gyroscope. It's just measuring, tilts and turns.
Right. It is something that we've explored: gyroscopy, accelerometry, magnetometry, right? Different sensors and what makes each tick.
That was a nice atom pun there.
Yes. Yeah, that was intentional. Thank you.
You get paid for that.
In February, Dr. Cox and his team developed the ability to detect the broadest frequencies yet with a novel quantum receiver. The group sensor is capable of analyzing the full spectrum of radio frequency in real-world signals, thereby unleashing new potentials for communications, spectrum awareness, and electronic warfare for soldiers on the battlefield. The sensor device leverages what are known as Rydberg atoms to effectively boost the portion of the spectrum of radio frequency being measured. The Rydberg atoms are sensitive to the voltage of a circuit positioned directly beneath the Rydberg atoms, which are excited by laser beams. Our question is simple. What are Rydberg atoms and what are they good for?
So you are uniquely qualified to answer this question. In terms of sensing, what are they good for?
Yeah.
And the second part of that is you've introduced an iteration of the Rydberg sensor about 9 months ago. Can you walk us through what's happened in the 9 months since in terms of that technology?
Yeah. So thank you for asking a question I can answer.
Yeah.
It's great. I thought you were going to ask me about what the soldiers are thinking as they.
That was my next question. Okay.
Yeah. So electrons have a negative charge. Sorry, I'm going deep here. Electrons have a negative charge. The nucleus has a positive charge. So when you take that electron and separate it very far, you have an electric dipole. Think of it as sort of like a bar magnet, but instead of a magnetic dipole, it's electric. So you have separated charge. That makes Rydberg atoms very good at detecting electric fields. In fact, for their density and size, they actually have the strongest electric interaction of any known material. So they are excellent, at least in theory, they are excellent measurements of electrical fields. And so at the Army Research Lab, this has been, and in my group, this has been one of our primary focuses for about the last 4 or 5 years. And in 2018, we published a paper that was one of the very first demonstrations. And so this has been a little bit even further back, one of the very first demonstrations of using Rydberg atoms to receive a communication signal. So that was a fun demonstration. Now, we didn't prove that they were state of the art, and at the time they weren't, but we showed that Rydberg atoms can be used as a quantum sensor to detect communications, and no one had ever used a quantum sensor in that way to detect quantum communication. So about 9 months ago, we wrote another paper where we used Rydberg atoms, and this is in Applied Physics Letters, if anybody wants to go and try to find it out on the interwebs, where we used Rydberg atoms as a spectrum analyzer. So we used them to detect ambient signals in the electromagnetic spectrum out in the air, all the way from zero frequency up to about 20 gigahertz, which is, a pretty high frequency, right? Included in there is GPS and satellite communications, AM radio, FM radio, the walkie-talkies of our maintenance team was in there, Bluetooth, Wi-Fi, was all in that range, and we could pretty much see all of it. And this was the first time that anyone had been able to use a quantum sensor to do something like that. So that was an exciting result for us. Again, there's still some work to make this sensor state of the art. It's not the best anyone's ever detected the spectrum, but it is the first time anyone used a quantum sensor to detect the spectrum. And the reason why that's important is because we expect that these exquisitely sensitive Rydberg atoms in the future, with more improvements, will in fact become state of the art. Mm-hmm. So maybe that gives a little more picture of why we're excited about this technology.
Yeah.
Yeah. So you asked that was more of a history lesson. You actually asked what's happened since then. And, I didn't want to answer that we've just been drinking coffee since then,
Yeah.
But no, there's actually a lot of activity. There's a lot of activity in the Rydberg sensing space. And so, this is really kind of blowing up. There's lots of new academic research groups. We hear of lots of companies that are entering this space, and lots of things are happening. I would say overall, the big push right now is exactly what I said. It's to take this technology from being a toy, from something that's cool. Oh, look, we used a quantum sensor and we detected the spectrum. That's really cool. But now we need to make it something useful, where we can do something better than it's done any other way. And we haven't done that yet. So that's the real current push. And it may not happen this year. This is a long-term research area. I think there's a lot of long-term promise, but, we often try to talk to our leadership and some of the great individuals in charge, and we ask for patience.
Yeah.
because these atomic technologies and quantum technologies are going to take time before they're fieldable. These are hard experiments. They require several laser beams. They require optical tables and lots of laser beam paths. And, it's going to take time before we can package this up and put it in a backpack, or even put it in a vehicle or an airplane, or, all sorts of places. So there's still a lot of work to do.
We're talking about new things, right? None of this is old hat.
Right.
Is there a template direction or a template path that has been charted already to take some of these toys and push them towards commercialization and even beyond, right? Beyond commercialization, we're looking at applicability. Has that ground been laid?
You asked about a path, if there's sort of been a path that, I think a great example that is fun to talk about is the chip scale atomic clock, the CSAC, which stands for chip scale atomic clock.
Yes. And
that is a commercialized device. It's actually one of the very few commercialized atomic devices that's really fieldable. You can put it in all sorts of things and it pretty much works.
Yeah, we have one here in the office.
You have one there in the office, right? And you use it to tell you when to go to lunch.
Yes.
But so that's a great template. That uses warm atoms, just like a Rydberg sensor. In fact, it uses rubidium. Typically, it uses the same type of atoms that the Rydberg sensor uses, either rubidium or cesium atoms. And so it's a great template. And it took a long time to make the CSAC a commercialized device. I don't have an exact history here, so, I'm going to be speaking sort of approximately, but it took a solid decade to take that CSAC from a concept and from really people knew it was going to work, but it still took 10 years to make it a reality. And it took a lot of money. I'm sure it was tens or hundreds of millions of dollars. It probably edged up to, over 100 million to put into research organizations and companies. And, it was just a really big effort of the past. And that is the type of effort level it really takes to take quantum sensors and make them happen out in the real world. On the other hand, it's not that bad. It really also depends on what kind of market we can find for these things, because for some markets, those numbers may not be, some markets, they don't bat an eye at those numbers. We think about, I Googled the other day, what's the current size of the quantum computing market? And my brain had a small explosion. It's like a $500 million market now. So it's hard to say. One thing I can say is that Rydberg quantum sensors are a little bit more challenging to package up than a CSAC, because it requires a blue laser that is not in the infrared or near infrared. It's about 480 nanometers, bright blue, and it actually needs to be quite powerful. So it needs to be at least tens of milliwatts. It also needs to have a very narrow line with laser, so a spectroscopy grade laser. So that laser in itself is pretty difficult to package. And of course, laser technology, probably something that your podcast listeners are well of. It's something we all rely on, and it's always getting better. There's laser development is kind of getting better around us, and we're going to ride that wave like everyone else.
Yeah, I wanted to talk about maybe integrated photonics being a driver, but perhaps the question's better asked with lasers being the driver. I'll let you pick either integrated photonics as sort of a theme or laser technology. How are one or both of those areas impacting what you're able to do down at ARL?
They're both really interesting. This sensor is a photonic sensor because we can have a Rydberg atom all we want. That's super great, but we're not going to do anything with it unless we have a very specific interrogation scheme that is done by at least 2 lasers, or maybe more. It can also be done with three photon excitation schemes or 4 photon excitation schemes. So it's really both interesting. From a big picture standpoint, we do dream of photonically integrated atomic sensors. This is a great dream that one day we won't have to have an optics table with lasers sitting on it and dozens of mirrors and polarizing beam cubes and modulators and all of these optics tools that fill up, an entire 10-foot table. But instead, this will be integrated onto a chip, and it'll be a tiny little optical computer with an atom sitting on top of it. And there's great work going on in that area that, maybe some of the people listening to this are probably doing that. And I would say, Rydberg sensors will benefit from this. Ultimately, all atomic sensors will benefit from this. Of course, it's not easy to photonically integrate 100 milliwatt, 480 nanometer laser beam. At least not to my knowledge. Maybe I'm not the expert. You may have someone call in and tell you I can do that, and you should have them call me.
This would be the podcast for it. Yeah.
Yeah, exactly. But overall, the photonic development and the photonic integration and the laser development are going to be important. So it's all important.
In the summer of 2021, Optica held its Optical Sensors and Sensing Congress. The Congress brought together leaders from multiple sensing disciplines, including the quantum space, among them Dr. Kevin Cox. The addition of quantum to the Congress signals the importance of the discipline, both in R&D and in real-world application. It also points to a future in sensing beyond that which is already known and understood. The Congress itself was a breakthrough event.
It was the first time, I believe, that this conference has ever had a quantum science session. So this was actually the sort of first quantum session at the sensing and, optical sensing Congress. That was exciting in and of itself. And I would say, I think I was really pleased with how it went, because we got to bring together kind of a kind of diverse group of people, some people working on atoms, some people working on photons. We had a fair number of people working also on defect physics, so nitrogen vacancy centers and diamond. And a fair number of these people were very applied and a fair number were very basic, so doing foundational science. And so it was a pretty rich setting, and I think it went really well. So I'm excited to see. I think I'm still, if they invite me back, I think I'm on the organizing committee for next year. I think, and unless I, they decide that maybe they don't want me to help.
Yeah, they're going to want to review. They're going to want to review this podcast. Yeah.
Yeah, exactly. Before they ask if they want me to help organize next year. But but it was really pretty fruitful, and so it was exciting.
There is great contrast between the speed at which quantum sensing takes place in the physical sense and the pace of related R&D. Rydberg atom experiments, for instance, are a long game. That doesn't mean work is halted. Instead, it raises an interesting question about the importance of trends and influences. It's what we asked earlier in our interview. What is driving the next wave of quantum sensing innovation? From there, another question arises. In asking it, we ask Dr. Cox to stare into the crystal ball and tell us what's next. Is entanglement the inroad to teleportation? Is astronomical interferometry for the detection of celestial objects quite literally on the horizon?
In what areas or, for what types of applications can we expect to see in the next wave of quantum sensing breakthroughs?
Can we call this like the investment hour? Like, is this the name of this one?
Yeah.
This is the investment hour. I have $1,000. What area of quantum sensing do I put it in? I kind of feel like the innovations of five years from now have kind of already happened, right? Mm-hmm. Anything that's going to come out 5 years from now has already been discovered. And maybe optimistically, I'm going to say very optimistically, Rydberg atoms are in that category. We've hopefully recently discovered that Rydberg atoms are useful, and it's going to take 5 years to start making that into a reality. But we get to get a little more creative if we talk 20 years out. And one of the areas that I'm really interested in, and this is one area that my research focuses in outside of quantum sensing, is in quantum networks. Quantum networks are basically networks that connect up lots of individual quantum particles, either be it atoms or ions or nitrogen vacancy centers or any quantum particle you can think of, and they're connected. Great. There's a photonics podcast. How do you connect up quantum particles? Well, you do it with light. You do it with photons. And what is the resource? There's a resource that's going to allow quantum networks to do things that classical networks can't do. And that resource is quantum entanglement. So quantum entanglement is going to be the informational resource, just like quantum computers, that is going to power quantum networks to do things that the current internet just cannot do. Now, we don't know what all of those things are. In fact, I would say this is really a further out technology, and quantum networking is very hard. It's hard to make entanglement persist over very long distances. But nonetheless, this is something I think quantum networks represent a new frontier with really transformational capabilities, disruptive capabilities, things that just fundamentally cannot be done any other way. We think about quantum teleportation, where we can teleport lots of information from one place to another at the speed of light without the information really existing in any meaningful way in between. And that will open up capabilities. I think one of those capabilities is long baseline interferometry that will allow us to do ultra-sensitive interferometry, perhaps for space, sort of extreme detection of celestial objects. You could think about exoplanets and things like that. It will, of course, the basic standard answer is this will allow fundamentally secure networking over long distances. And of course, that's very important for lots of reasons. But ultimately, I think when we can really harness entanglement over long distances, there's going to be capabilities that we can't even wrap our tiny minds around at this stage. So that's one of the ones that really kind of gets me excited at night.
So we take a lot of pride in being information breaking podcast, and you heard it here first. Quantum teleportation, quantum entanglement, and ultra-sensitive interferometry are hard. So
they're hard, yeah, but they're exciting, right? They're hard. Yeah.
All right. Well, Kevin Cox from ARL has been our guest. Kevin, I appreciate your time. Thank you so much for being here.
Okay, thanks, Jake.
It's time for the Luminary Minute, a segment where Photonics Media looks back at a pivotal figure in the history of optical and photonic science. This episode, we'll be taking a look at Ernst Abbe, inventor of the apochromatic lens, the Abbe condenser, and a significant contributor to optical theory. Born in Eisenach, Germany, Abbe's rise to optical prominence started with a move from academia to industry. The former lecturer at the University of Vienna launched a collaboration with Carl Zeiss in July of 1866 aimed at creating a water immersion objective with a resolution equal to those demonstrated by competitor Emil Hartnack. In his career, Abbe introduced a number of innovations to the design and manufacture of microscopes. In 1886, he created the apochromatic lens, which eliminated both the primary and secondary color distortions experienced by prior microscope design. The Abbe condenser, invented in 1870, greatly improved illumination. Abbe, with Otto Schott and Carl and Robert Zeiss, would form what would later become Schott AG. Abbe would succeed Zeiss as head of Carl Zeiss AG. In 1889, Abbe set up and endowed the Carl Zeiss Foundation to run both Carl Zeiss AG and Schott. As head of the company, Abbe instituted significant labor reforms, including overtime, sick pay, vacation time, disability assistance, profit sharing, and an 8-hour workday. That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.